Good, thanks very much.
Sorry,
Good morning, everyone. It's a real pleasure to have an opportunity to share our work on Centre-Vortex structure of QCD ground state vacuum fields and understanding the quite surprising impact of including dynamical fermions in these gauge fields. The work that I'm going to focus on is done in collaboration with James Biddle, Wasim Kamli, Emily Troartha, and Adam Virgili. So let's get started. I thought maybe the best way to get going is to just remind ourselves of the standard picture of the QCD ground state fields. And we've got an image here, a chunk of space that's maybe big enough to hold 2 protons. This is a lattice 24 by 24 by 36. And there are 24 frames in what I'm calling the time dimension. And I'll show that to you, but I guess we need to just start by saying that if we just look at a chunk of empty space, we see field fluctuations at all scales. And if we want to see the non-perturbative physics, then we need to go in and smooth out the short distance physics. I'm going to start an animation here, and this animation uses a highly improved cooling. It's order A to the 4th improved cooling to remove short distance fluctuations. I've done about 25 sweeps here, and now I'm showing you the 4th dimension. So this is the energy density. Think of it as the chromoelectric and chromomagnetic field strengths squared and summed. And of course, the celebrated feature here is that you see a lumpy vacuum structure which resembles instantons. So what you can do if you want, if you're curious, you can fix these gauge fields to Landau gauge, and then you can go in and examine the field structure. Of course, in QCD, there are 8 chromoelectric fields and 8 chromomagnetic fields. And so you're looking at a handful. Well, here we are with the chromoelectric field number 8. Going back to field number 1, we're slowing down the frame rate here so that you can see the structure. Hopefully it's transferring from this side of the world to your side of the world without too much trouble. I will mention that if you want to see this without the lag, half a world away, you can go to YouTube and the videos are there. Just do a Google search for CSSM visualizations with an S in the Australian standard. So this field, we're having a look at it. We're sort of nice in that you've got some instantons or anti-instantons sitting on the edge of the lattice, so you can have a look at the field structure and how that changes as a function of time. We thought somewhere maybe we should show all 16 in some detail, and so they're all there on YouTube should you have the patience to watch it. I'm going to jump ahead to where we start talking about the topological charge density. So let's do that. So here we are superposing the topological charge density on top of the action density and going back and forth, just to note that they align very well. The old saying was, you got to be where the action is. And sure enough, you do. And you can then examine the field structure and how that lines up with the topological charge density. Of course, we're excited about this because we know that these instanton-like objects generate low-lying eigenmodes in the Dirac operator. And in fact, at low energies, the most probable place to find quarks in the vacuum is on top of these structures. And we know that it's those interactions then that break chiral symmetry and generate mass. And so it's a very important phenomenology that forms the groundwork of modern understandings of vacuum structure. But what I'd like you to do today is just entertain the possibility that there's something more fundamental that actually captures the salient features of QCD, that of confinement and the dynamical generation of mass through chiral symmetry breaking. So I'm going to ask you to consider center vortices in the ground state QCD vacuum fields. We'll start off just by explaining what center vortices are, and then with about 4 slides, I'm going to try and capture your interest and invite you to entertain the possibility that this is interesting. We'll look at static quark confinement, the gluon propagator, the quark propagator, and chiral symmetry under modified gauge fields by modifying the center vortex structure. But then we'll actually dig in and we'll examine, what do these center vortices look like? We'll be looking at things like percolation, monopole, secondary loops, singular points. One of the best references so far is this one. And then finally, we'll ask the question, what is the impact of dynamical fermions on the center vortex structure? And how does this, impact on the phenomenology of the center vortex model? So the bottom line is we want to try and understand what is the origin of dynamical mass generation and confinement in QCD. In fact, do they even have a common origin? Okay, so I'm going to spend a lot of time talking about vortices. Let's start with the vortices that we know and love. This is a couple of nice pictures of what we would call thick vortices, in that there's material that's swirling around. I would love to show you the thick vortices, but I'm not going to do that because it's pretty complicated. What I am going to show you is the vortex line that sits at the center of these thick vortices. And in 3 dimensions, it's just a line, but in 4 dimensions, if we were to imagine picking up this coffee cup and moving it around, that line would, of course, map out a sheet in 4 dimensions. So vortices are sheets in 4 dimensions, but just about everything I show you is going to be a 3-dimensional slice of the 4-dimensional world. So in 3D, center vortices, they're tube-like topological defects present in the QCD vacuum, and I'm going to be showing you the thin vortex lines, the center lines. And you can sort of think of that, if you wish, as the axis of rotation of the thick vortex. And there's a nice cartoon here that shows a center vortex, this dashed line in a QCD gauge field, and it intersects with this lattice plaquette, and we're going to have a recipe that allows us to identify the fact that a vortex has, in fact, pierced this plaquette. So how do you do that? Well, on the lattice, remember that the gauge field, the gluon field, is encoded in terms of the link variables. So it's an exponentiation with the coupling, and the lattice spacing here makes this dimensionless. So this is a 3x3 complex special unitary matrix. There are 8 degrees of freedom then. And because you're looking at a vector field, these link variables are, of course, then associated with the links of the lattice, so that when you're at a particular lattice site, you can head off in the, well, here drawing the y, z, and t dimensions. So step 1 to find vortices, you perform gauge transformations, and your goal is to bring the links as close to an element to the group center as possible. Simply put, you're trying to make the link variables the identity, okay? So the center elements of SU3 are the 3 cube roots of 1. So we're trying to make, here's the identity, and here's a phase that describe the 3 cube roots of 1. And I'll regularly refer to M here being within the set of -1, 0, or +1. So how do you do that? You introduce a gauge functional and you perform gauge transformations to maximize this. You can see we're summing the trace of the link variables, and mod squared just makes it clear we don't care which phase we get. We simply want these links to become as close to the identity as possible so that we can capture the information that we're after. So this process is called maximal center gauge, and everything I show you today will be in maximal center gauge. Here's how it works. If we look at the trace of a link variable, we can separate that out into a real part and a phase. Of course, the phase goes from -pi to pi. And I'm introducing the field variable phi here with the 3 cube roots of 1 present. So phi will be in this range, and we're expecting it to be +1, 0, or -1. Now, before gauge fixing, you've got fairly a good population of all sorts of phases. But after gauge fixing, it looks pretty good. This is a logarithmic plot. And so perhaps to show you how good this process is, here it is without the logarithmic plot. So you really, really can bring these these link variables very close to the identity. Of course, there's supposed to be some shoulders there, and you can still see them. All right, so that's the maximal center gauge part. Step 2 is you actually replace those link variables now by one of the 3 cube roots of 1. So we still have the identity. We have one of the 3 cube roots of 1 here, governed by this field variable m mu of x, which again is -1, 0, or +1. So this is the projection then. So we're replacing 8 degrees of freedom in the link variables, now down just by one of the 3 cube roots of 1. I can't imagine anything more fundamental than this in trying to understand the essence of QCD vacuum structure. How do you identify vortices? Well, then you examine the product of these projected field variables around the elementary square, and each plaquette then takes a value from Z3. And if we have that Z3 value being different from 1, i.e. m is going to be plus or minus 1, then we say that a vortex has pierced that plaquette. So that's how we find them. Maximal center gauge, a projection, and then products around plaquettes to see if something interesting happened. Here's a really nice cartoon of what it might look like. The tube here is describing a thick vortex and the QCD vacuum fields, and the zigzaggy line here is the vortex path embedded within that. And it's that vortex path that I'm going to be showing you. So in doing this, you can then create 3 sets of configurations. You can have the original configurations, which we refer to as untouched. We're not doing anything to them at all. You could just, instead of looking at these, you could work with the vortex only configurations. So most of those links are the identity, except for a few where m was plus or minus 1. That's the information that's contained in the vortex only configuration. And the other thing you can do is take the original untouched configuration and multiply by the complex conjugate or Hermitian conjugate of the vortex. That will necessarily remove all vortices from the original fields and leave you then with a vortex removed field. And so you can study these 3 different field configurations to try and understand what the role of center vortices is. So in doing this, I'm going to be showing you 4 ensembles. The early things that I show you will be just a 20 cube by 40 pure gauge lattice. I've got used to looking at these things now, and these look pretty simple to me. But I'm also going to show you some 32 cube by 64 lattices, drawing on the Dynamical Fermion work from the PAC-CS collaboration. And we're grateful for them sharing those configurations generously through the ILDG. And we've also created a pure gauge configuration to match the lattice spacing and let us understand then the role of dynamical fermions versus the pure gauge sector. All right, so I promised I'd try and motivate your interest in center vortices. So let me touch on some ancient history. One of the first things that people looked at was the static quark potential. And this, of course, is looking at the potential energy between 2 massive static quarks at some separation r. And it serves as an indicator of confining behavior in the form of a linear long-range potential and a Cornell potential. I'll be using this to draw some lines through the data that I show you. So this is really early work back in 2011. This is the untouched gauge results. If you remove vortices from the configuration, you get this set. So we were excited that we lose confinement. There's no linearly rising potential here. But if you try to recreate the static quark potential with only the vortex degrees of freedom, people were disappointed in that you only got about 2/3 of the string tension. And that was seen very much as extremely disappointing and perhaps a failure of the center vortex model for the vacuum. Another thing you can do is look at the lambda gauge quark propagator. It's supposed to have this form. There's a renormalization function, which tends to be infrared suppressed. The more interesting thing is the mass function, and it shows dynamical mass generation for small values of the momenta. And so we can look at that. I'll be showing you results from the overlap Dirac fermion action for all sorts of good reasons listed there. So this is in the early days. Again, this is the pure gauge theory. And the untouched mass function looks like this, and lots of dynamical mass generation present. If you remove the vortices, you lose most of that, and you're left around 100 MeV. So it was seen as promising, but again, disappointing. Removing vortices didn't remove all of the dynamical mass generation, and that was disappointing. You can look at the vortex only mass function. There, you do have to do a little bit of smoothing on the configurations to satisfy the smoothness condition for the overlap fermion action. But after 10 sweeps of smearing, you can see that the untouched and vortex only configurations agree reasonably well. The other thing we looked at was the restoration of chiral symmetry. So we were expecting that hadrons related by chiral transformations to become degenerate. So these are the pairs we looked at. We did an extensive analysis. It's published here. I won't show you the results because it's too boring to look at all of these mass plateaus. But what you do need to know is that at like quark masses, all symmetries were restored. At heavier quark masses, where you have explicit chiral symmetry breaking from the quark mass itself, we had an interesting phenomenology that looked like non-interacting constituent quarks. Okay, so let's get to what do these things look like. So I need to render this information. So what I'm going to do is I'm going to render vortices with these jets. So I'm going to use a right-hand rule. So if I've gone around a plaquette here in the X and Y directions, and I found an M equals +1 vortex, I'm going to then render that in my illustration with the jet pointing in the Z direction, and I'm going to make it blue. On the other hand, if I've made the product of the Z fields around the plaquette and I find -1, then I will plot the jet in the opposite direction and I will render it red. This seemed like a reasonable thing to do for our first look. And here's a 20 cube by 40 pure gauge lattice. And that's what the vortex structure looks like. I remember the first time I saw these, I thought it looked pretty complicated, but I've got used to it now. And I think the characteristic features in the pure gauge is that you have this vortex structure, but you can see within it, there are large voids where there are no vortices. One of the things you might want to have a look at is a simple vortex path. So down here, we can see that there's a link path that runs around here and comes forward. If it ends, that's the periodic boundary condition. It'll come out the other side of the lattice. So that's your typical vortex path. What else did we see? There's vortex intersections where you'll have vortex come in, it actually goes down and around this loop and then comes out. So they're fairly common. What else do we see? We see monopoles where 3 vortex paths will come into a cube on the dual lattice and finish there. And at the same time, there are of course corresponding emerging 3 jet things. So that's the kind of structure that we saw when we looked at it. Maybe it's interesting to try and quantify the kinds of things that we've seen. So if you think about the number of vortices entering a 3D cube on the dual lattice, one possibility is there's none, so there's no vortices within that dual cube. You could have a terminating vortex, but that's forbidden by the Bianchi identity. So if you see that, you've got an error. You can have 2, which is just a vortex line flowing through the cube. You could have a monopole with 3, with 4. That would be some sort of vortex intersection. We saw one of those. 5 would be a combination of a vortex intersection, or maybe a vortex line flowing through a cube and a vortex monopole. You could have that coincide, or you could actually have 6 coming into the cube, 1 in each face. And that could be either vortex intersections or double monopoles of some sort. So with that introduction, this is how they're distributed. So first of all, about 90% of the plaquettes, 90% of the cubes on the dual lattice are empty with no vortices running through it. We're happy to report that we had no terminating vortices as required by Bianchi. About 8% of the elementary cubes have vortex running through it. Then you're down another order of magnitude for the branching points or the monopoles. I'll use branching point or monopole interchangeably. Then here's the intersection point, and then these are fairly rare, but they do exist where you can have 5 or 6 jets coming into an elementary cube. So that's the distribution of the kinds of things you see. It can be quite interesting, some of the structures that you can see. This is a different time slice of the same gauge field. Look at this. This is fascinating. This is a little cluster of monopoles. So there's one here. There's 3 emerging here. 3 emerging here. There's 3 coming in here. There's another one over here. What we've learned by doing correlations with the topological charge density is this kind of clustering is a great way to get large values of the topological charge density. And there's a fairly strong correlation then with these branching points or monopoles and topological charge. Okay, so what happens when you go from the pure gauge sector and you start including dynamical fermions? So let me set this up. We looked at this a long time ago in the standard picture where we were just looking at visualizations of the topological charge density. And one of the things you may have heard is that the topological charge density forms these sheets. It's like 2 pieces of paper with different colors crumpled together. And sure, you can see that if you render the topological charge density all the way down to 0. But what I've usually done is just rendered the peaks of the topological charge density so you can see in the configuration. If you smooth it more, then yes, you have instantaneous, well, these yellow and green blobs will annihilate each other because they have opposite topological charge densities, and you'll have larger, smoother objects appear as you do more and more smoothing. So on the next slide, I'm going to show you this kind of smoothing. So not too much smoothing at all, just enough that we know that our operators for topological charge are sensible. And we're doing a comparison here of the pure gauge and milk 2+1 flavor QCD gauge field configurations. In the 2+1 flavor, the light quark masses were 27.1 MeV. So this is looked at quite a while ago. What was it? There we go, 2008. And can you tell which one is quenched and which one is dynamical fermions? So I'm not sure I can hear you. If you said the top one was pure gauge, you're absolutely right. The reasoning is that if you have well-separated instanton-like objects, then you're going to have 0 modes in the Dirac operator. And if you have 0 modes in the Dirac operator, the fermion determinant is suppressed. And so this is bad for dynamical fermions. So the vacuum responds in a couple ways. One thing it does is it makes the instantons and anti-instanton-like objects a little bit bigger, and it increases the density of them as well. And that way you have overlapping objects and you don't suppress the fermion determinant. So there we go. A long time ago, we could see the impact of dynamical fermions on vacuum structure. Let me show it to you now for center vortices. So this is now the pure gauge lattice, but it's a little bit bigger now. We're looking at 32 cubed by 64. We can probably see the same qualitative feature in that there are large voids within this. You do have vortex paths. Some of them are different colors, and that's just because there's one very large percolating cluster, which I've got colored in blue here. And then there are occasionally some smaller loops, like there's one there, and there's one over here that isn't connected to the percolating cluster, and it's kind of fun to look at those as well. In fact, there's a big loop here that's not connected to the percolating cluster. So we'll have a look at those in a minute, but that's the qualitative features of pure gauge theory, but looking very similar to the lattice I showed you. So let's go to dynamical fermions now. And maybe I'll just go back and forth. That's pure gauge, that's dynamical fermions, right? That's pure gauge, dynamical fermions. It is qualitatively extraordinarily different. And it's so densely packed. If I show it to you from the outside, it's very, very difficult to really make out what's going on. My preference is to actually get inside the configuration so that you're only looking about half of the information at a time, and then maybe you can begin to try and make out the complexity of the structure that's here. But it's a huge change to the Centre-Vortex structure in the process of introducing dynamical fermions. Here's one of these disconnected loops that's not part of the percolating cluster. Let's have a look at the structure of that. So here we are in the pure gauge sector, and you can see that there's very little going on in vortices that aren't connected to that percolating cluster. There's probably only 2 structures here that are worth looking at all. In dynamical fermions, it's very different. Again, that's pure gauge and that's dynamical. So all of a sudden, you've got all sorts of small structures within the percolating cluster, and there's some very interesting ones to look at. Let me pick out a few. So here's one of the features that I thought was interesting. So right away, you can see that, again, this branching structure is very prominent in full QCD. So in fact, all of the loops I think that I'm going to show you will have monopoles in them. So here's one here in that simple structure. And there's another one here. Again, the prevalence of these branching points for monopoles and anti-monopoles. They are very abundant upon introducing dynamical fermions. So there we go. I think we've seen all of the most interesting structures on here. So that's what center vortices look like. It's complicated, but a few qualitative features are maybe worth highlighting. And that, first of all, the vortex vacuum is typically dominated by a single large percolating cluster. And once you introduce dynamical fermions, you have a significant increase in the number of vortices that are observed. And to quantify that in pure gauge, you're typically looking at a little over 3,000 in that 32 cube by 64 lattice. But you go to full QCD and you almost double that. So it's a huge change. And we also saw that the secondary loops that we looked at, they're much more complicated. And there's a lot more of them. So one of the things we did was we thought, how do we quantify this structure? I mean, now that we've seen them, we get some sense of things to quantify. So what we're looking at here is a histogram of the vortex path lengths just within the percolating cluster that I was showing you. So I've got the pure gauge in orange here, and I've got the dynamical fermion results in blue. And what I mean by path length is it's the number of jets from one branching point to the next. And these distributions are normalized by the number of paths that we've looked at. So what you can see is that for moderate sized paths, in both cases, you have an exponential distribution. And one way of interpreting what that means is that you could say that there's a fixed probability of branching. So as you know, imagine yourself being one of the vortex paths. At each step, there's a finite probability that you'll branch through a monopole or any monopole structure. And so this exponential distribution is consistent with the idea that you have a fixed probability of branching. The other thing about the exponential distribution then is that the branching is independent of how far you've traveled through the gauge field in the process of doing this. Okay, so what about the impact of dynamical fermions on the center vortex structure, the gluon propagator? So let's have a look at the gluon propagator. All right, so when we're studying the propagator, we're looking at d of q squared, which is typically written as a renormalization function over q squared, because at tree level, the gluon propagator goes like 1 over q squared. So we're going to consider the renormalization function simply by multiplying the gluon propagator that we calculate on the lattice by q squared. And the renormalization, we pick a value of q squared where we set it equal to 1. So it's somewhere out here in the tail of the distribution that will renormalize our propagators. Of course, one of the early...
A moment, there are 10 minutes left, including discussion.
Excellent, okay, thank you. So one of the early celebrated features was that the introduction of dynamical fermions screens the propagator, and it does so quite dramatically. And so we can see that here. Of course, the question is whether vortices can capture that information. So here we are in the pure gauge sector, and we have the three fields. The untouched is in the green here. Vortex removed is in orange. Vortex only is here. And we used a linear combination of the vortex only the vortex only here and the vortex removed here to try and reconstruct the propagator as best we could. And so look, there's some suppression, you know, in the vortex removed, but it wasn't that good. So I don't know, not such a successful model for separating out perturbative and non-perturbative physics. So moving on to dynamical fermions, we get a very, very different picture. So the original shows the standard infrared enhancement, but if you remove vortices, you get this orange curve. And so there's almost no infrared enhancement anymore. And that has now been separated out into the vortex only. So we see a much cleaner separation of perturbative and non-perturbative physics, possibly. Here it is for the lightest ensemble, the same thing. You can see that the dynamical fermion screening effects have in fact been captured in the vortex only configurations, and that we go from the pure gauge to the 701 MeV to the 156 MeV with the screening of that captured nicely by vortices. We can also look at confinement by taking the one-dimensional Fourier transform of the gluon propagator and constructing this wall-to-wall correlator. The excitement about this, though, is that C of t is negative, suggesting that the spectral density here then has negative contributions. It's not a positive spectral function. And so since a physical state does not have a negative norm contributions in its propagator, there's no Callan-Lehman representation, and the corresponding states then don't appear in the physical particle spectrum. So this is our signature for confinement in the gluon propagator. And here's what we see. Let me just, because of time, let me jump straight to the 701 here. So we do see in the untouched configurations that we have positivity violation, as we expect. But the interesting thing here is the vortex remove configurations don't dip into the negative values, at least in a statistically significant fashion. So it admits the possibility that the vortex remove dressing function is just perturbative, and that the vortex only, it definitely picks up the positivity violation and confinement. So I think that's interesting. Similar thing for the lightest masses. The quark propagator. So we've already looked at that. I showed you before that vortex removal got rid of most of the dynamical mass generation, but now for dynamical fermions, it's pretty much eliminated. If you remove vortices, there's no dynamical mass generation whatsoever. So that's very exciting. And we've just recently had our very first look at the ability of vortices to provide dynamical mass generation in full QCD. And in fact, it's certainly able to do that. So how about the static quark potential? So here we are in the pure gauge sector. Maybe the most interesting thing about these plots, remember this is untouched, this is vortex remove, the loss of confinement, this is vortex only. This plot down here shows the local slope from Fitz to V of R over a window of plus or minus 3/2 the lattice spacing. And so you can see the old problem that the untouched string tension is here. The vortex only string tension is about 2/3 of that. But again, this changes very nicely. You introduce dynamical fermions. Now The string tensions between vortex only and the untouched agree, and there's no evidence of any confinement potential in the vortex removed. So again, a much nicer picture, complete satisfaction. So we would argue that center vortices are the origin of confinement in QCD. So just to wrap it up quickly, first of all, we've seen that center vortex structure is complex. There's all sorts of monopoles in SU3 with further enhancement when you introduce dynamical fermions. There's always a long distance percolating structure, and it's a huge difference in the number of vortex links. And we've also seen that even the small paths become much more complicated. So yeah, the introduction of dynamical fermions radically alters the center vortex structure of the vacuum fields, and it really improves the phenomenology. So if you remove vortices, it suppresses the infrared enhancement of the gluon propagator, it eliminates dynamical mass generation, and it eliminates the confinement potential. It really does that very nicely now. And in the consideration of vortices alone, you capture the important infrared physics that you're after. And so we conclude that center vortices provide a common origin for both confinement and the dynamical mass, the generation of mass by chiral symmetry. So we would argue center vortices capture the essence of the non-perturbative QCD vacuum. Thanks for your attention.